Hello everyone, and welcome to the start of vectors. Now vectors is we're done with the heavy trig. Doesn't mean we're totally done with trig completely, as you'll see shortly, but it's not going to be as intense as it's been in chapter 6. So to start out our study of vectors, we have this first video, and the skill objectives for this video are: number 1, represent vectors geometrically and algebraically. Number 2, find the magnitude and direction of a vector. Number 3, add and subtract vectors. We're going to do this both geometrically and algebraically. And same with scalar multiplication on vectors. That will also be done geometrically and algebraically. We're going to find unit vectors, and we're going to express a vector in terms of its horizontal and vertical components. Conceptual objectives. Number 1, understand the difference between scalars and vectors. And number 2, relate the geometric and algebraic representations of a vector. Let's start out with some definitions, shall we? The first one is a vector is a directed line segment. Okay, we will use these vectors to represent quantities that have a magnitude and a direction. A couple examples of those are velocity, which has speed and direction, and force, which has a weight and direction. For example, let's talk about velocity versus speed. When we talk about the speed of a car, it might be traveling at 60 miles per hour. That's the speed. It has a magnitude. That 50 miles per hour is the magnitude. Whereas if we talk about it in terms of, oh, it's traveling at 60 miles per hour west, now we have a speed, a magnitude, and a direction. The west tells us which way it's going. Where if I just say the car is traveling at 60 miles per hour, I don't know which way it's going. Okay, so that's one thing that you have with a vector. It's going to have the two quantities associated with it. The real number quantity, that magnitude, another name, what that is actually, that's called a scalar. And it's a real number used to represent the magnitude. Now, when we have a vector, remember it is a directed line segment. We will have an initial point, which is at A, and a terminal point, which is at B. And it looks, a lot of times people confuse vectors with the geometric figure known as array. The difference between a vector and an array is that a vector, by being a directed line segment, it does have these end points. A vector starts at A and ends at B, where a ray in geometry continued on and on forever. So it would start at A, but then it would just go off in this direction, just keep going. Okay, that's the big difference. Now, when we talk about a vector, you're going to have to name that vector, and you have a couple different ways to do it. One way to do it is using the end points, the initial point and the terminal point. And so one way to name that is going to be A, B, and then you'll have an arrow above it. Often you'll see math professors, math teachers, we too tend to get a little lazy sometimes with writing it. So you'll see it like this, like kind of a half arrow above it. Another way to do it, and this happens a lot in textbooks, is they'll use a lowercase letter. And they'll make it a boldface. In fact, in this video, you're going to see it shortly where I name a vectors using bold type. You can't necessarily write that. So another way of writing this would be calling this like vector U, and we'll put that little vector symbol, that little arrow above it. So that's another way. Otherwise, if it was in print, that would just be a bold U without the symbol above it. But since we can't write in bold, when we do it when we're doing problems on our homework or on the board or at any time, we'll use this symbol right there above the single letter. Now, the next thing we have in terms of this is magnitude, and magnitude is the distance from the initial point to the terminal point. And it's denoted with this like an absolute value. And see, you notice the bold type that I've used for U in this situation. That is denoted, this is the magnitude of vector U. Now, our book uses this notation. I know the IB math book uses that notation, but I have seen some books that instead of that notation, it would be like a double absolute value sign. So they'll have this. that would be the notation for the magnitude of u. So keep in mind both, that you could see those depending on the situation, what we're working with, and what textbook you have, and they just happen to mean the same thing. Now the next thing we have is what will determine what it means for vectors to be equal. Two vectors, u and v, are equal if and only if they have the same magnitude and the same direction. Let's take a look here what that means. In this case, I have, in this first situation right here, I have these two vectors here. This one vector will be u, and this vector will be v. In this situation, those two vectors have the same magnitude and they have the same direction, so therefore they are equal. We would say, in this case here, that vector u is equal to vector v. Now let's take a look at situations where the vectors are not equal. In this second case that we have right here, we have two vectors. We'll call this first one A and the second one B. And in that situation right here, they have the same magnitude, but they don't have the same direction. So therefore vector A, in this case, is not equal to vector B. In our third case, we'll call this first vector C and this vector D. Now, in this situation right here, again, they have the same magnitude. Notice, though, they have opposite direction. Where in case one here, they both had the same magnitude and were pointing in the same direction. In this case, these two vectors here have the same magnitude, but they're pointing in opposite directions. And because they are going in opposite directions, they would not be equal. So I would say here that C is not equal to D. Now let's take a look at the geometric way of looking at vector addition and subtraction. With vector addition, in this case, in the first case here, where we're going to take vector u plus vector v. In this situation here, and in this case, the white vector is going to be u, the pink vector will be v. What we use, one way to do this, and what I typically use, is what's called the tail to tip method for the geometric addition. Okay, so what's going to happen here? I'm going to take vector u, and I'm going to place it at some location. And then at the tip of vector u, which is right there, I'm going to put the tail of vector v. And so I move that right here to the tip to the tail. And then the vector that is actually the sum of these two vectors is going to be the vector that goes from the tail of vector u to the tip of vector v. So it's going to end up being this vector right here. It starts at the tail there. It's going to go over to here. And that will be the vector u plus v. Now let's look at vector subtraction. So in this case, what we're going to be looking at is u minus v. And when we want to do that, what you're going to do, again, you're going to go and place vector u at some location. But this time what you're going to do is you're going to put vector v, put the two tails together. So they're going to be at the same spot. And so, in this case, the subtraction of the two vectors is going to be the vector that goes from the tip of u to the tip of v. And so, in this case, it's going to be the vector that goes from here, let's pretend that's a straight line, to there. That is going to be vector u minus v. Really, the main thing you have to realize is the difference in terms of doing these is looking at the difference in terms of the placement of the vectors. When we add the vectors, you use that tail to tip method. That's the idea there. And when you're working with the subtraction, put the tails in the same location, and then the vector that is the subtraction of the two is going to be the one that goes from the tip of the first one to the tip of the one being subtracted. The other operation that we have is what's called scalar multiplication. And scalar multiplication is going to be some real number k times a vector u. And so what I have here is, here's vector u. Now when I take vector 2u, it's scalar, it's going to go and scale that vector. So if I do 2u, you're going to get a vector that's in the same direction as u, but that's going to have, the magnitude is going to be twice as long. So this would be vector 2u. When I do vector 1/2 u, now what's happening is that the magnitude of this is it's going to be in the same direction, but the magnitude is going to be half of what you see for vector u. Now the other thing you have is that scalars can be, because there can be any real number, they can be negative. And when you see a negative, what you have is that the vector is actually going to go in the opposite direction. And so some of the things to remember in this case. Since k can be any real number, things to keep in mind is that if the absolute value of k is greater than 1, then this vector is going to increase in length. The magnitude. If the absolute value of k is less than 1, that's going to decrease the magnitude. Spelled that wrong, but you got the idea. And then if k is a negative, if k is less than 0, it's going to change the direction. Now let's take a look at the algebraic interpretation of a vector. Now one of the things you have to keep in mind is that vector, remember vector equality just depends that the two vectors have the same magnitude and the same direction. So location is not part of that. And so what you'll find is that we can, like we had with angles, we can talk about the standard position of a vector. And the standard position of a vector is going to be one where the tail of the vector is at the origin. Now when we put it in that spot, our terminal point, our initial point is going to be at 0, 0. Our terminal point is going to be at the point AB. AB. And so what we have here, this distance is A, that distance is B. Now that does allow us to go through and help us define a couple things. Now the first thing you're going to note is that when we talk about this, we can get to what's called the component form of the vector. And the component form of vector u is going to look like this. It's going to be A, comma B. Notice the symbols that you see for that. There is another notation you'll see as well. Sometimes you might see it, I don't think you'll see it in this book necessarily, but in other things that we do, and we'll call vector u. The other one would be like this. Those will be the two notations I will use when we talk about vectors. Now the other thing you have with this is because of where we're at, we can definitely find the magnitude. The magnitude of vector u is really, remember, it's the distance that we are it's the distance between the terminal point, the initial point, and the terminal point. So in this case, the magnitude of vector u is just going to equal this square root from the distance formula of a minus 0 squared plus b minus 0 squared. Or it's equal to the square root of a squared plus b squared. That's the magnitude. The other thing we have, thinking about this, is that we do have, when we look at this, we do have a direction angle here. That will be theta. And given that information, you'll notice that we are dealing here with a right triangle. And so I can say that the tangent of theta is equal to opposite over adjacent, so it will be B over A. So now make sure you have those two, the magnitude and the fact that the tangent of our direction angle is equal to B over A. And let's take a look at a couple of examples on things that you will see happening in the problems that you're going to have to work on. What we have here are three vectors that I need to find the magnitude and direction angle for each one of these vectors. So let's take a look at the first one. In the first one, I know the magnitude of u, that's going to be this, is equal to the square root of 3 squared plus 4 squared, which equals the square root of 9 plus 16, which gives us the square root of 25, which equals 5. So in this case, the magnitude of u happens to equal 5. That should be a u there. Now let's look at the direction angle. The direction angle, I know that from the previous slide, I know that the tangent of my direction angle theta is going to be B over A, so that's going to be 4 over 3. And so what I need to do at this point, to find the direction angle, I just take the inverse tangent of both sides. So I take theta equals the inverse tangent of 4/3. Now because for the vector u happens to be in the first quadrant, we're not going to have any problem. So I can just do the inverse tangent, just pull my calculator, do inverse tangent of 4 divided by 3. And remembering to put this into degree mode, I get that this comes out to be 53.13 degrees. So my direction angle in this case is 53.13 degrees. What I'd like you to do right now is I would like you to go pause the video and I want you to find the magnitude and the direction angle for number 2 for vector v. Welcome back. When you did this this particular problem for vector v, found the magnitude, you should have got that the magnitude was 13. The magnitude of v is going to be 5 squared, a squared, plus negative 12 squared. Now remember that to put that into parentheses, especially if you put in your calculator, and that when you do 5 squared plus negative 12 squared, it's going to come out to be the square root of 169, which does equal 13. Now the direction angle for this one, even though we look at this like we said in the first part, that in that vector u, we didn't have to worry about anything because we were in the first quadrant. Well, this one in vector v, we are in the fourth quadrant. And again, we don't have to worry about anything, but because remember, the inverse tangent is going to give you an angle that's between negative pi over 2 to pi over 2, or negative 190 degrees and positive 90 degrees. So in this case, when our terminal side is in the, or when our angle lies in the first or fourth quadrant, we don't have anything to worry about. I can just go set this up. We know that the tangent of theta in this case is going to be negative 12/5. And so when I do the inverse tangent of that, I get that theta comes out to be negative 67.38 degrees. And that's fine. That can be our direction angle. If they want a positive direction angle, what you would have to do is add 360 degrees to get to a positive direction angle for that vector. But every problem I've ever had to work with, having a negative direction angle is fine. Now we get to number 3. What I'd like you to do right now is find the magnitude of vector A. So pause the video, find the magnitude of vector A, and then when we come back, we'll talk about that direction angle. Welcome back. Now in this case, let's just deal with the magnitude of vector A first. We'll deal with that quick. The magnitude of vector A comes out to be the square root of negative 1 squared plus negative 3 squared, which will be 1 plus 9, which equals, so therefore the magnitude of A is just the square root of 10, and we're not going to be able to simplify that. Now let's take a look at the direction angle. Now in this case, I know vector A, the term that vector A lies in quadrant 3. And this is going to be the same issue you have if it was in quadrant 2 as well. In fact, the example in the book dealing with this is a vector that does lie in quadrant 2, and you can take a look at that one on page 697 of your textbook. But what happens on this, because the inverse tangent will only give me an angle from negative 90 degrees to positive 90 degrees, and those angles lie in either quadrants 1 or 4, we need to go through and use the fact that the period of tangent is 180 degrees, or pi, to go and find the angle that actually will be in quadrants 2 or 4 2 or 3 that we were looking for. So in this case, we're looking for one in quadrant 3. So when I do the inverse tangent in my calculator of negative 3 over negative 1, which becomes 3 over 1, that is equal to 71.5, basically about 5.7 degrees. Well, now what I have to do in order to go and find the angle in quadrant 3 that would have that, to find that angle, I will need to go and add 180 to that. And so when I add 180 degrees to 71.57, I get my true direction angle. So in this case, theta is actually equal to 251.57 degrees. That's the direction angle for our vector A, which is the vector negative 1, negative 3. So what you have to keep in mind on this, when you're dealing with a vector that is in quadrants 2 or quadrants 4, or quadrant 3, when we place it in standard position, when you do your inverse tangent to find the direction angle, you're going to have to add 180 degrees. Now let's take a look at the vector operations that we have. We know vector addition and scalar multiplication. Those are our two main operations. And so in this case, I have two vectors, u, which is the vector AB, and vector v, which is the vector composed of c and d. And so if I take vector u plus vector v, really what I'm going to do is what is probably would be the natural thing that you would think about is I'm going to take the first components and add them up, and it's going to be the sum of the second components as well. When I do scalar multiplication, when I take k times vector u, I'm going to go through and multiply. I'm going to take k and I'm going to multiply it to both components of vector u. So I'm going to get the vector ka and then kb. Let's take a look at some other problems like this. In this case, I do have two vectors. One is the vector u, which is 3, 4, and vector v, which is the vector 1, negative 5. And so the first thing I want to do is I want to find the sum of u and v. So in this case, I'm going to have the vector 3, 4 plus 1, negative 5. And what we saw last time, I'm just going to add the first components. So 3 plus 1 is 4. And I'm going to add the second. So 4 plus negative 5 gives me negative 1. So the u plus v gives me the vector 4, negative 1. Now when I take negative 3 times u, so it's going to be negative 3 times the vector 3, 4. And really I'm just going to multiply each component by the negative 3. So I'm going to get the vector negative 9, negative 12. When I do vector u minus v, so I'm going to take 3, 4, that vector minus 1, negative 5. And in this case, very much like the first one when we added the 2, now I'm just going to subtract the corresponding components. So the first component is going to be take 3 minus 1, which gives me 2. And 4 minus the negative 5, 4 minus the negative 5 is going to be 9. Now the next thing you have to keep in mind on this is that we are able to do all sorts of things with this, and so we can go through and do other calculations. I can take 2 times vector u plus 3 times vector v. So that's going to be 2 times the vector 3, 4 plus 3 times the vector 1, negative 5. Which when I go and deal with the scalar multiplication, I deal with that first. I'll get the vector 6, 8 plus the vector 3, negative 15. And when I add those together, 6 plus 3 is 9, and 8 plus a negative 15 is going to be a negative 7. And that's what we end up having when we go through. That's how we end up going and doing vector addition and scalar multiplication. Next, we have some algebraic properties, and these should be somewhat familiar to you. The first property here is that vector u plus vector v is equal to vector v plus vector u. In other words, vector addition is commutative, and in the second one, it is associative as well. So the group, we can change the order, and we can group them in different ways. Also, scalar multiplication. Scalar multiplication, we can go and multiply the two scalars and then multiply that result by the vector, or we can go and put one scalar with the vector and then multiply that result by the other scalar. In other words, it is associative. Scalar multiplication is associative as well. Also, we have some distributive properties here. If I take a scalar times the sum of two vectors, I can distribute that scalar to each vector and add that result. And if I'm adding two scalars and multiplying that result by a vector, I can distribute the vector to each scalar, find out those results, and then add the two resulting vectors. We also have some other things that we get to deal with. First up, we do have what's called a zero vector. Keep in mind that the zero vector is the vector 0, 0. So if I take 0 times a vector u, I will get the 0 vector. If I take 1 times a vector u, I just get the vector itself. If I take negative 1 times a vector u, I get the vector that has the same magnitude as u, but in the opposite direction. And the last thing we have is if I take a vector and add the opposite of that vector, the result will be the 0 vector. Now again, these are all properties. You've seen similar properties to that as you were working in Algebra 1 and Algebra 2. So these should look somewhat familiar to you. And it really just says that a lot of the calculations, the way you've done calculations before, will still hold here with vectors as well. Now here's a little bit more dealing with Traeger. We're going to deal with finding what's called the horizontal and vertical component of a vector. The horizontal component of the vector is A, and the vertical component of the vector is B. Now, one thing you have to keep in mind is that our vector u right here, it has its terminal side at the coordinates AB, terminal point, and the length of this vector is equal to the magnitude of u. So I have this length is magnitude of u, this length is A, and that length is B. And of course, we do have a right triangle. We do also have our direction angle here. And so what I can say from SOHCAHTOA, from what we've seen in the past, that the cosine of that angle is going to be adjacent over hypotenuse. So I get A over the magnitude of u. And the sine of that angle is going to be opposite over the hypotenuse. So I'm going to get B over the magnitude of u. Now solving each of these for A and B, I will find that the horizontal component of our vector is A is equal to the magnitude of u times the cosine of the direction angle. And the vertical component of our vector, B, is equal to the magnitude of u times the sine of our direction angle. Let's now take a look at an example. Let's say the magnitude of our vector v is equal to, let's say, 6, and theta comes out to be, let's go 100 degrees. Now, even though now 100 degrees would not make a triangle similar to what we see here, these formulas do work for any angle, so we can use that. So I know, in this case, my horizontal component, in this case, A, for our vector v, A is going to be 6 times the cosine of 100 degrees. And so again, making sure your calculator is in degree mode, I put that into my calculator and it comes out to be equal to negative 1.04. And I'll just take it to 2 decimal places. And I know B, that vertical component, is going to be 6 times the sine of 100 degrees. So I take that, put that in my calculator, and I come up with, that's going to be 5.91, let's go 91 when I round that off to 2 decimal places. And so therefore I can say vector V is equal to the vector negative 1.04, 5.91. The next part of our discussion is really going to what's called a unit vector. A unit vector is any vector with magnitude equal to 1. So what you have in this case, and this is how we find a unit vector, if a vector V is a non-zero vector, so in other words, it's not the vector 0, 0. So it's going to have a direction, it's going to have a length. Then U, which will be our unit vector in this case, is equal to the vector V divided by its magnitude, or taking 1 over the magnitude of V and multiplying it by vector V. That is going to be a unit vector in the same direction as vector V. Now, what you have to keep in mind here, if I need to find a zero vector, I can just go through and I can multiplying any non-zero vector by the reciprocal of its magnitude will give me that unit vector. Let's take a look at an example that we have. In this case, we want to find the unit vector for the vector 1, negative 3. So the first thing I need to do when I'm going to find a unit vector is I have to find the magnitude. So the magnitude of the vector 1, negative 3, we know is going to be the square root of 1 squared plus negative 3 squared, which we have that as being the square root of 10. And so our unit vector here is going to be either go through and take the vector 1, negative 3, divided by the square root of 10, or I can think of it as 1 over the square root of 10 times the vector 1, negative 3. The result is that I'm going to get the vector 1 over the square root of 10 and negative 3 over the square root of 10. And if I want, I can go and rationalize that. That will be square root 10 over 10 and negative 3 root 10 over 10. And that would be our unit vector. Now we do also have 2 other special unit vectors, and they are the vector I, they're lowercase I, and that is the vector 1, 0, and our lowercase j, which equals the vector 0, 1. Now, what's special about these is these are unit vectors, but they go either vertical or horizontal. The I is the vector that goes in the positive direction along the x-axis, 1 unit along the x, and j is the vector that goes 1 unit along the y. So what that does for us, though, is it does give us an alternate way of writing a vector. I can take, for example, I can take the vector, let's just say the vector 3, 4, and I know that's going to be 3i plus 4j. And so if I have a vector, if I say vector u is equal to, we'll do that 3i plus 4j. And I say vector v is equal to 2i minus 5j. We can take u plus v by really just combining the like terms. So 3i plus 2i is going to be 5i, and 4j minus 5j is going to be minus 1j. And so the result would be the vector 5, negative 1. Now you're going to see both representations here with this, and so you need to be ready to be familiar with that, and really you can choose which way you prefer it. But just you do need to be able to recognize what's happening with both notations. Now with that, the next thing we have are applications. And of course, we're going to do This video I know is probably getting very long. I haven't seen the time yet, but the examples for application problems will be done in class. And so that's what we'll do next class, along with kind of taking some of the stuff that we've done in 2 dimension and also deal with 3 dimension as well. So with that, I hope you found that this was, while it was a lot of material and it was a little bit longer, I hope you found that the material was fairly easy. So we'll see you in next class. Have a good night. Have a good weekend. See you then.